to the next panel on the topic of performance portability. To start us off, I just was going to throw up a few view graphs to stimulate conversation and discussion. So first off, I thought I'd play a little game, take a few view graphs. The idea is I'm talking about performance portability, but I'm using old witticisms that hopefully some of you recognize. So the first one is, the purpose of computing is performance, not portability. What's the actual, anybody remember what the actual witticism is? Close. The purpose of computing is insight, not numbers. That's by Hamming. This one might be a little bit easier. You can have moderate performance with maximal portability, or you can have maximal performance with moderate portability, but you can't have maximal performance with maximal portability. Anybody recall that witticism? Well, that's Abraham Lincoln. You can fool all those people some of the time, or some of the people all the time. Sorry, I thought this would be funny. I'll try one more. I must be portable only to be performance. Well, that's Shakespeare. I must be cruel only to be kind. And then finally, performance you can carry with you. Okay, there was a great article in HPC Wire I just happened to find back from April of this year that I thought did a decent job of trying to describe what performance portability is, or what it might be. And then finally, some questions that I thought of that maybe just to stimulate discussion. So again, these are my questions. I'm happy to kind of start off with a couple of them, but the point of the panel is for questions for all of you on the topic of performance portability. So I'll just ask one of these here, and it won't be the first one since that's quite probably controversial. But was Fortran 4 back in 1964 an example of performance portability? So asking the panelists here, do you have any thoughts when Fortran, the first Fortran implementation was introduced, would you have considered that an example of performance portability? Yes or no? Maybe? Anyone?
So I would consider that as an example of performance portability. So when we look at performance portability, we're looking at how can we have basically a single source implementation. So an algorithm or a simulation program run across as many machines that we're interested in, as many different architectures or hardware implementations that spans our area of interest, and give close to optimal performance on each one. So for example, we may have complex instruction set machines, Intel processor based supercomputers, and we may have RISC reduced instruction set based supercomputers. Architectures are fundamentally different, but Fortran 4, you can do a single source implementation. You write the code once, you compile it on the CISC architecture, you compile it on the RISC architecture, and you get good performance on both using the same source. So I would say that it's portable. You have a single source implementation that you're compiling across the different architectures you're interested in, and then you get good performance on each architecture. Now, do you get near the theoretical peak performance? Not typically, but there's not a lot you can do in that single source implementation. Anything you do to improve performance on one architecture may decrease the performance on another. So you kind of want, portability, and then you want good performance across the different platforms of interest.
So along this line is, in addition to the programming language, and then for parallel computing, the communication layer, for example, standardizing the message passing layer using nowadays everybody uses MPI, which is a big advancement. I remember in the early days for different machines, for Intel machine, we have to use the Intel syntax to do send receive, and another machine we have to change the syntax. So that really hurts the source level portability. You cannot have a single source code to run on every machine. And similar to the this portability issue is the standardization of lower level library effort. So for example, like a BLAS library, which helps to abstract a lot of linear algebra lower level operations to be in this standard interface API. So all the vendors, they start getting engaged, accept this standard, and then implement on a specific machine so that from the user level, you don't need to worry about how your vector operation, lower level matrix multiplication, whether it's fast, it's guaranteed to be fast if the vendor is helping in this regard. So there are a lot of advances in parallel computing along this performance portability path.
So just quickly on the Fortran 4 question, I would say compilers are an important part of performance portability. I wish it were the only part, but it's an important part.
Sure. Okay, so that was one of my questions.
I have one comment on that,
Brian?
which is Fortran 4 was performance portable in space, but not in time, right? It lent itself to poor software engineering practices. And as a result, how much Fortran 4 do we really have around here? How much are you being taught Fortran 4? It lends itself to terrible programming techniques. So it's not here today. One of the things that kind of drove a stake through it was we went to distributed computing. So while we were all in vector and shared memory machines, Fortran 4 was easy to compile for, but the compiler couldn't reason about distributed memory very well. And so we had to. And once we had to, now we all had much bigger codes. I think the main impediment to a code being portable, so there was a person who, in some sense, I was always dismissive of, and now I've come to have deep respect for. So Jeff Hammond never worried about this. He says, I don't care what your programming model looks like, I'll just program to it. And I was like, how do you do this? How do you stay ahead of it? And I realized he has 20,000 lines of code, and that's it. Every time a new machine comes along, he just rewrites his code. I'm like, so.
Which code are you talking about?
Well, his tensor contraction kernel, right? Tensor contraction kernel that is in the kind of at the base of NWChem and other machines like that, other algorithms like that. And he just throws it away. And it's an amazing freedom he has. So he's almost the epitome of what people are now referring to as agile computing. He has agility.
Well, but does literally rewriting, and given that I understand the argument is a small algorithm, but does literally rewriting that algorithm in every particular context you want it to run, is that considered performance portable?
His algorithm and him and his science are. His code isn't. But maybe his code doesn't have to be. The other part of this is, that little kernel is maybe that's 20,000 lines embedded in NWChem or in AMD, which is millions of lines of code. But those millions of lines of code aren't executing much. So maybe you only need to be performance portable in a little bit of your code, and that's like a defensive programming, where you really make sure that everything funnels into a very small part of your code base, and that's the part you keep rewriting every time a new machine or a new compiler comes along. All the rest of it, all of your abstractions and your file handling and all your other stuff, you just get to carry along in whatever language you like. Python, I don't care. But there's a little bit of your code that's where your code spends 99% of its time. Make that part small and get everything to funnel into that one part. And that's the part you can throw away and rewrite and throw away and rewrite and have branches and postdocs and students rewrite it and give it to the computer scientists. Because every time you're going to be writing your code, making it run fast, you can get some computer scientist coming in and say, let me see your kernel. I don't want to see your big ugly code and blah, 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 blah. I want to just take your kernel, make it run fast, and write a paper. And then that's the last you're going to see of me. So I call it strip mining. They're going to come in and strip mine out your computer science part and make that fast. So be ready for it. Have a piece of code that's ready to get strip mined. And then some computer scientist or some compute center will come along and say, can I see your kernels? So have kernels ready to go.
Okay. All right. Questions? I know we had one or two questions yesterday that sort of leaned towards performance portability. I forget who was asking them. Okay, do people have a general sense of what we mean by performance portability, especially in the context of the architectures that are coming online? Things like GPUs and many core. And do GPUs and many core make Boy, I'm out of time. I'm sorry. The GPUs and many core. Well, let me just ask this of the panelists: to what extent? Given the example of Fortran 4, which I use, the reason I use Fortran 4, back in the mid-60s, everybody was writing assembly code, and different processors required different assembly code, and so there was literally no ability to share code that you were writing. Fortran 4 abstracted that. It was a great solution at the time, but it had many weaknesses as well, as Brian mentioned. But today, if you look at the differences between, say, GPU execution and many-core execution, that is radically different. Those two worlds are radically different. So for the panelists, does the architectural differences between those two types of processing suggest performance portability challenges that are either cannot be solved or cost a lot more to be solved today?
So I'll step back just a little bit and talk from some personal experience. So me and my team work deliberately with an abstraction layer to manage this main processor, host, device type of an architecture. So what we have done is we come back, and when we think about it, we look at, we're going to run a multi-physics code across a modern exascale machine. And embedded in that thought is that we're heading towards this architecture that you can break down into an abstraction that is basically the host processor, probably an Intel, a classic Intel processor, and then some sort of a device that is adjacent to it, may or may not share memory with it. And this device could be an Intel mic, it could be a GPU, it could be just a bunch of Intel cores, or it might be something else that we're not seeing yet. So our challenge, at least me and my team's challenge, is we work in the area of complex multiphysics code, so they're engineering analysis applications, and we would like to be able to write that code and then maintain that code because it's expensive and it's large. And we'd like to write it and maintain it and have it evolve with a minimum cost and a minimum effort type of a strategy forward in time as the architectures change. So we're very interested in a single source implementation. We write the code, and then maybe we just recompile it on each new architecture that comes along. Well, that's an ideal, probably unachievable idea. So what we do is when we write this code, we are using an abstraction layer. In fact, we personally use Cocos from Sandia that allows us to manage this abstraction of the host and the device. So we will have our host code, most of our multiphysics application currently runs on the host, and then we will offload portions of the work, kernels of the work onto the device, and we write that code at an abstraction layer that we don't really know what device is going to run on, GPU, mic, processor, so on and so forth, and rely on the underlying compiler and the Cocos interface to manage the host to device data transfers and the execution model on the device. So that's kind of our abstraction layer that we work to, and as programmers and developers of these analysis codes, we program to that abstraction layer and hope that Cocos and the compiler vendors for the device and the overall architecture will accommodate that model as it changes. So that's our overall strategy.
Any other strategies for this? So Sherry, I know that you've looked at, dealing, I guess, directly with, I don't know, are you making CUDA calls directly in SuperLU? Or?
Yes, indeed. That's at the moment. We haven't put much effort in terms of adding the abstraction layer to this work. And we know about Cocos, but we just haven't got around to investigate. So one of the performance issue in general, for example, in linear algebra library, and in particular in SuperLU, for example, is there are a number of parameters right now. Even in scalar pack, SuperLU, all these libraries, these number of parameters are exposed to the users. So it's a user's responsibility to change the block size depending on your machine and your sparse matrix pattern. But this is quite a burden. Then if you're talking about performance portability on different machines, then you with the default parameter setting, you actually could get quite a different compared to the default parameter setting compared to the best parameter setting. You could get the speed difference easily 2 or 3-fold difference. And talking about GPU, in sparse matrix, as I mentioned, there are a lot of dense blocks we try to extract internally, but depending on the sparsity pattern, the dense blocks, they are not a uniform size. They can vary a lot. For smaller block size, it's really not worthwhile to put them to do computation on GPU because your transfer time easily overrides the benefit of doing this small data parallel stuff on GPU. So for small size, you really need to keep them on the CPU side. But right now, we don't have intelligent decision, automatic decision making built into the system, so that user doesn't need to involve in this decision making. And that's one of the things we're working on the proposal to DOE, hopefully to get all these exposed parameters from different libraries, including hyper, PET-C, trilinals, etc., so that we can build at the top level, higher level software layer, we can build an intelligent system to query the underneath machine hardware and also to query the sparse matrix characteristic in order to to give the user a good decision-making mechanism. So that's the one step forward in terms of doing more performance portability automatic way.
So I saw Rob grab the mic for a second. Any questions about the last two responses from Glenn or Sherry on COCOS? Okay, I had a follow-up for the both of you before you, Rob. At one time, I was interested in applying COCOS in the context of SuperLU. And I know COCOS has a sort of a data structure, an array model in it somewhere. But what I realized very quickly was SuperLU had a very optimized representation for arrays that have a lot of zeros in them, basically sparse representations. So the question is it practical in that context to try to apply COCOS within SuperLU? Glenn?
So it might be. So at the time, COCOS had a fairly simple flat array structure. That it's and the reasoning behind this is you're working with an array, and in fact, it's you think of it as the same array on the host and then on the device. Now, if the host and the device are basically one and the same, if they're both Intel processors, that may be the same array, the same address and memory space. So as you look at storing your data in this flat array, call it A and 0 to 100 in length, you store your data in there, and then when you read it in the device code, it's the same shared memory location, so you're just reading from the same array in the same order. So what you do, though, is if that device is, say, a GPU, there may be a host to device memory transfer involved that COCOS does behind the scenes. And not only that, it may change the layout of the memory to where you're striding on it when you're storing your data in your array on the host, you're storing it in an efficient way. You want to be able to read from it in an equally efficient way on the device. And the mechanism and the logic for doing that may be fundamentally different if the device needs to access memory in a different way. So COCOS handles that translation for you, but in doing so, it makes some assumptions about what is in that array. And in the early days of COCOS, it was just a flat array. Now there are CSR arrays in COCOS that you can use and base your code on. So there's two choices. One is to build, to use a flat array, and you as a user build in your knowledge of what how that array should be accessed. If you want the CSR type of the structure, then you build two arrays, you manage it yourself on the host and on the device, and you handle that higher level access. So that's one strategy. The other strategy is just wait for the abstraction layer vendor, in this case COCOS, to give you some of the fundamental types of arrays you'd like, or request them, like CSR. CSR is very common, so that's now in COCOS. So COCOS handles the data transfer if needed between the host and device and back, and it may just be just passing an address if you're in the same memory space. It also handles the different execution model that may be on the device versus on the host. And so those are really the two pieces of capability that are in that abstraction layer that we use.
Okay, Thanks.
So in sparse code, in addition to the array-based parallelism, data parallelism, if you want, we actually need a lot of task parallelism mechanism. So that's in addition to a lot of parallel computing, the construct.
Okay. I'm sorry, Rob, I interrupted you. Go ahead, did you?
Yeah, I'm not sure where to start. There's a lot to say about performance portability, but some of what Sherry said about parameters was a good point, actually. We often think about compilers and getting sort of fast node performance for a given piece of code, but if time to solution, for example, is the thing you want to get, then sometimes it affects the algorithm you run or on the machine. So on a parallel machine with a slow network, you might choose different parameters, which runs a different mathematical algorithm, but gives you better performance than you would on another machine. Now that we're also moving into this realm of everything's highly parallel, that affects a lot of the kinds of algorithms that we can run, versus in the old days where you could have a lot of sort of sequential type code that would run perfectly well on the architectures at the time, and actually you get good performance out of it. So it's not simply performance portability is not simply just getting an implementation to run as fast as it can on different architectures. It also affects the algorithms you develop and all these sorts of things. So.
Okay, well, we haven't heard saw many hands go up for questions. So again, I want to encourage everyone here to ask questions on the topic of performance portability. I'm guessing a lot of you are pretty tired this morning from having survived the first week of the training, but this is a great opportunity to ask questions on this topic. I think performance portability will become more and more important as we move forward with these newer architectures. VJ over here.
Okay, so as we talk about performance portability, we're looking at the algorithmic aspect of it, but from a science aspect. So say, hypothetically, I have two different algorithms. One is really amazing in terms of communication costs and things like that, but not very accurate. The other one is very accurate, but poor in terms of parallel efficiency or in the way you can parallelize the algorithm itself. So basically what I'm getting at is that your algorithm choice has a huge implication on how it will perform, and also a huge implication on performance portability. So one algorithm can easily be run on a multi-core system and a GPU architecture or something, but another algorithm is only good for a multi-core system, but absolutely horrible on GPUs. And when you have these kind of really complex decisions to make, because finally the decision is what's going to stay for the long term. So how do you make those kinds of decisions?
I would say algorithmic and mathematical superior algorithms will remain superior. It is worth investing your time in making that good algorithm scale as much as you can. Many people waste a lot of their life and a lot of their time with scalable algorithms, but they really don't extract much science. It's the better algorithm doing the better science. Do not get too caught up in the fact that you're not using the whole exascale machine. That better math wins out almost every single time. These kind of embarrassingly scalable algorithms don't tend to generate much good science. Stick with the good algorithm, find a good mathematician and a computer scientist, present them with the challenge. Say, look, this algorithm is clearly superior for this and this and this reason, and I don't think I can get this to scale. You'll be surprised how people will think about your problem and change it for you. So stay with the good math, stay with the good algorithms. You will almost always come out ahead with this way.
But what do you do when the good math and the good algorithm, it sort of falls on either one side or the other, especially between, say, GPU and many-core?
Oh, we have horrible motifs like, say, branch and bound, or graph walk algorithms, which look at their face to be purely sequential algorithms, right? There is no parallelism there. You know, we have found parallelism and we have found multiprocessing within those algorithms many, many times. And that has resulted in great advances. You know, you tell Google, web search used to be thought to be a, spectral, it's a, spectral algorithm. It's like, well, that's just a big parallel algorithm, big sequential algorithm that we have. We found new algorithms. We found new ways of executing that mathematical algorithm. You know, computing is much more flexible than you think. And it's okay to use the processor fairly inefficiently if it's a good algorithm. Don't worry about the fact that you're not getting reordering and there's not that many threads that can be running. You know, many times the most important thing is you're using the DRAM bandwidth efficiently. That's, everyone worries about, have you decomposed well enough? And it's like your performance model will tell you it's the DRAM speed. That was the only thing that was important. If I have 4 cores on Edison running at once and I'm bandwidth limited, that's it. That's as fast as you're going to go. Congratulations. Truly over decomposing massively parallelism is not always the key to getting it right.
So I've been talking about this concept of a single source implementation for the device code. So you want to have an adequate amount of parallelism available in the device code. These are typically, in the case of a GPU, a very highly parallel device. So you need to have underlying parallelization there to be able to run efficiently on the device. There's also variation in what is best for thread-to-thread synchronization across the different types of devices. So you might, I've been talking about, well, we have a single source implementation, so we write the code once and then we just recompile it for the different devices. Well, that's only going to really run optimally probably on one of those device choices. So let's say, for example, that you're not that interested in a single source implementation. Maybe you want, some basic C++ code, rely on the compiler and the vendor's operations to compile that on, the Intel platform and a multi-core platform. And for a GPU, you want to write a custom implementation. So now you have, a single source for most of the devices, but one specialized source that you want to optimize for the GPU. Say you have high-performance CUDA code. Well, what you'd want to have there is some sort of a generic template interface that will allow you to use a single source implementation across most of the devices that you'll come across. But then you want to be able to specialize that template to accommodate this this customized GPU code. So that's what you're looking for. You may want a single source over most of the devices, but a specialized template instantiation for GPUs, for example. So your abstraction layer, you'd like your abstraction layer to support that type of a strategy.
So when you talk about the optimal algorithm always prevailing, so better math will prevail. How does this fit together with a lot of people still using second order algorithms on a large scale? So probably most engineering applications today are still second order. So we know there are higher order approximations.
I give a whole talk on this at some times, which is, the kind of roofline model, which is higher arithmetic intensity, more accuracy per byte, because moving the bytes around is what costs you. And I have people in my group running second order algorithms, even though I have fourth order and sixth order available. And what often happens is that strong nonlinearities or multi-physics couplings, if any part of your algorithm is second order, your whole algorithm is second order. And so it's very easy to fall off the high order pinnacle. And that's why engineering codes where they have everything in the kitchen sink tossed in there and there's some kind of zeroth order piece chucked in there along with it, you're lucky to get first order out of I will occasionally see Fluent get second order, occasionally. Usually I'm seeing first order with most engineering codes because you pop open the hood and all it takes is one boundary condition done wrong and you fall off. But it is going to be more important, and I think a consistent push to get all of your algorithm up the curve on higher order will pay off. It'll pay off on the little machine. It'll pay off on your on your laptop. It'll pay off on the big iron. the property of time to the DRAM and time to the registers and time to the the L3, that profile of time is the same on all the machines: laptop, wrist phone, exascale machine. And that's where you pay the price, and it's true at any scale that you're computing. So higher order is a win. It is hard. Sometimes you do not use another person's package because you can't control this.
So a follow-up to that, though. In Chambo, if you do have this dial, second order, fourth order, sixth order available, and there's a multi-physics code that's using the Chambo framework, isn't it a simple matter of just tuning the dial to sixth order and say, well, everything that you were running at second order now run at sixth order in the code? Or is that not?
In AMR level, there is a section that says, what is your physics, please? And they write it. So when they write their own MHD, or they do their own Hall term, or they do their own, they do resistivity in a different way, any of those modules done, it's a callback, right? You extend the package by callbacks. All your callbacks have to follow just as much rigor. That's why I think this style of Chambo fortran I've been showing you is not the way to go. I think a higher level of abstraction is going to be needed to help people stay up on the pedestal.
So one motivation for the higher order is to have less data, to less memory and less data moving. But generally, we need more data that is required by the physics. So we need more refinement, and that has. So how do you think that these two come? So, so you need more refinement, you need more data structure in.
So do you chase accuracy with adaptivity, or do you chase accuracy with order, right? Higher order or more refinement? And it is, the answer is yes, you do both. Adaptivity is for where you have highly localized phenomena. If you have highly, if there's shocks, interfaces, star collapse, various factors, you can chase it with adaptivity. Adaptivity plus higher order does have a bigger win overall.
Yes.
So, there's a sweet spot typically. So typically for a factor of 4 refinement ratio, fourth order tends to be a sweet spot in terms of how much time you spend doing these kind of interlevel operations versus how much time you spend, getting the good answers. So, a fun metric to do is you take a kind of a plot file or an output file and you run a compression code on it, right? Run it through gzip or fzip or something. If that file compresses a lot, then you had very low information, right? So the visit guys are always complaining, when I need to move all your files, nothing compresses. I hate your code. I can't actually move things fast because it won't compress. So that's a good thing. Not being able to compress the file indicates there's lots of information in it, right? Well, there's not much to squeeze out. So that's the kind of metric you use kind of after the fact. So a second order code, fourth order refinement tends to compress more. So you actually haven't, like I said, AMR is compression at the algorithm level. So you can kind of do this kind of back of the envelope check and just run it through a compressor and see, am I in a sweet spot or not? And, maybe I need higher order, maybe I need more adaptivity.
I'd qualify that a little bit. gzip does not, notoriously does poorly on floating point data. So you do have to apply compression algorithms or adjust your data a bit so that gzip can compress it well. Or
I use, Peter's, fzip or something, right?
Which is lossless. Aren't lossy. Which is lossless. Aren't lossy, which is lossy.
Yeah.
Gzip is lossless.
But there are,
if you
Virture has lossless compression. Like there are lossless floating point compression schemes.
There are, yeah. But let me ask, were you talking, pardon me, were you both talking about basically the difference between, I've heard these terms H adaptive and P adaptive. Is that basically what you were talking about? Yeah. Okay. All right. Another question. Over here, EJ?
I will say that P adaptive is what gets you higher arithmetic intensity. It is the one that gets more accuracy per byte. H adaptive, they're both going hand in hand. So I've been trying to push people to higher order, because that's a better use of the platforms in the future.
So going back to the abstraction layer, kind of approach to making the software, your software more performance portable. Many, I feel like to be able to build a good abstraction layer over this, you need, I mean, often it's achieved with a lot of experience. You're able to design your software in the correct way, but many times, I don't know, as a graduate student, you're thrown into a big piece of a large piece of code, or you're about to start building your own large piece of code, and it's probably the first, second, third time that you do this. So, what do you recommend as to take a look at good, I don't know, examples out there, or good references that can teach you this in a quick way or in an intuitive way? Because even in computer science, the curriculum, very few curriculums teach you that. And many years in industry or in academia or in national labs is what might teach you that, but some graduate students cannot afford that or when you're starting.
So our experience in developing, these portable performant libraries and applications, we're just at the beginning of that trajectory today. So there's not, this isn't widely practiced. There aren't really, there isn't one or two commonly accepted models or approaches at it. It tends to be application specific in some cases, how you do things and how you structure the application. So we're just in the learning stages as a community to how to do this, as the architectures and as the applications get more advanced. So it is a bit of a challenge right now. There are some examples out on the internet. So the Trilinos package that we work with at Sandia, there are a few examples in there on how to use Cocos and how to structure a Cocos application for a linear solve or maybe a Krylov, a Newton-Krylov type of a solution. There's some simple examples out there, but for the application that you're ultimately working with, that, the abstraction that you see in the examples may not fit what you're looking to do. So it is, basically where we're at as a community, we're still, in the early stages of experimentation, how to design support libraries that use these abstractions, and then how to put together and design, engineering analysis applications that will use those libraries or that will use those abstraction layers. So there are a few examples out there. The best way to get started is to look at those examples and write some code and get some experience with it, on simpler applications and see what works best for you. So there really isn't a consensus model about how to do this. So it's very, we're in the early stages, and experience, getting some experience in how it works for you is probably the best suggestion.
So I don't have ideas for references to sort of point you to. What Glenn was talking about was focused more on kind of the challenges that are emerging right now. But we've been doing performance portability for a long time, really, and the challenges just change over time. And I think a lot of what we've learned in the past can also be applied today. So, and there are some simple things like, don't write your code so that it relies on a standard that's coming out right now and there's hardly any implementation for it. That's something that will, kind of stay back a little bit. Don't make your code too reliant on something like that. But you can experiment with these things. Isolate kernels. This was brought up earlier. Just some of these kinds of things. So the BLAs have been around for a long time as an example. The basic linear algebra subroutines. This goes way back, and it was a way of trying to achieve performance portability. The idea is that when new architectures come out, you rewrite these little kernels, and your code performs well. Or you get the vendors to implement them for their individual machines. So I think there are lessons that can be learned from the past that still apply today. The architectures now are much crazier, and the issues seem a lot more challenging than ever before. And a lot of what Glenn said pertains to that.
Let me, you asked the question within the context of graduate studies. How many attendees here are in graduate programs of one form or another with the ultimate responsibility of probably writing some code as part of your thesis work. So question back to all of you then. Given a choice between writing, say, portably performant code that is easy to maintain, that you might be able to put up on GitHub and has an enduring legacy that others could contribute to, but might take you 6 months to a year longer to develop, versus writing the quick and dirty hack that gets the results out and you can publish the paper, how many people would choose to delay their graduation 6 months to a year to write that more robust, portably performant code? Anybody? I see 1 or 2 over there. Wow, I'm impressed. I know when I was faced with that challenge, I ended up, basically having to hack the code together to get the results out I needed. And ultimately, people took what they learned from that and actually developed a real solution that was useful in many contexts, as opposed to the one machine I had access to at the time. It's a tough question, I think. Very, very difficult. Okay, we've got about maybe 10 minutes left. Any other questions on the topic of performance portability? Even thoughts, wisdoms? VJ over here in the back.
Hi. Well, I'm not even sure if my question is technical, but you see heterogeneity everywhere. Whatever that you take, whether it's the software stack or whether it's the hardware stack, so you have FPGAs, GPUs, CPUs, and everything. So what I see it as is it's very difficult for me to visualize if a certain piece of source code would give the same performance portability, would give you a performance portability. So is it even reasonable for us to expect that the source code is going to be performance portable? And shouldn't the applications or the languages quantify performance portability?
Wow, quantifying performance portability. That's a metrics for performance portability. That's a tough one. Panelists have thoughts on that?
Usually when performance portability comes up and you ask the question, what is performance portability, it takes hours of debate and nobody can agree. So metrics I think are really hard because it's hard just to agree on what it is.
Even when things are well defined, metrics are hard. And I think certainly, yeah, I've been in meetings where, in fact, I've been in meetings in which the specific topic for the all-day meeting was performance portability, and we left at the end of the day and there was very little agreement in the room on what it actually meant. But I wanted to amplify what I think I heard Rob said, is that, we've faced tough engineering challenges throughout the history of scientific computing, going all the way back to the 50s and 60s. In fact, I have customers at Livermore. Some of the code that they execute today was actually written in 1959. Basically that same code. I mean, and it was exactly that code up until about 10 years ago, to be honest. And I'm talking about just sections, kernels, as a fact. So, tough software engineering challenges then require creative solutions. And what I see as performance portability is just good software engineering. That's my perspective. And the current challenges are extreme, but I think there will be good software engineering solutions to those, such as the things Glenn mentioned, Cocos, another project at Livermore called Raja. Has anybody heard of Raja in here? Okay, Raja's one in the back there. So Raja's another approach, somewhat similar in spirit to what Cocos is trying to do, but loop-level parallelism in codes, a little bit more like sort of OpenMP-like solutions. But good software engineering.
I do think that's independent of for a particular compute kernel that you're going to do, however you've ordered the loop or written the iterator or visited the elements or moved over the array, there's a more fundamental performance model that you can look at, which is, how much data are you going to touch? Where does that data have to come from? How many operations are you going to do on it? And that kind of arithmetic intensity or ops per load store can give you some idea of how fast could this go. And then on particular platforms, you have different kind of architectural ratios, how much DRAM speed, how fast is the shared memory, do you fit in a cache line? Well, that's your working set, right? How much data does this kernel touch from when you enter to when you end? And did the kernel before me load that in? That tells you about roughly how much data is being accessed. And then how fast can you load and store it, and then how fast can you do operations on it, you can get a pretty good idea of how fast that piece of code could go, given the hardware that you're going to look at. Then the rest is, how well does it get implemented? So, if you're in a piece of code where it's completely dominated by, you do very little operations on it, and it's mostly, you're going to touch a lot of data, well, then the machines get off a lot simpler, right? It's how fast is your DRAM, how fast is your interconnect, and how fast can you move the data around? So all these vectors and fancy things and synchronizing and threading and looping, who cares? It's just how fast can you move the data. There are a few kernels out there in your codes where the data movement is not the limiting factor. Now everything else is all in play. I think you just need to think about where the data is going to move, how fast you're going to move it around. That gives you a pretty good idea of how fast your code's going to go. So for a lot of you, that first order performance model will tell you most of what you need to know.
All the portable programming paradigms like we have, like OpenMP or MPI, tries to express parallelism on an algorithm level, but we also try to combine and the hardware aspect and try to expose the parallelism to an hardware level. So instead of doing that, do you think having another layer which exposes the hardware level to the algorithm level would help? So instead of trying to combine the algorithm level parallelism and trying to expose it to the hardware, do you think we can have another layer in between which just exposes the hardware, but the algorithm level parallelism is just trying to expose the parallelism on an algorithm level?
That almost sounds to me it may be a little bit like what Cocos is trying to do. I don't know if that's a true statement, Glenn. Can you?
So it's for performance, you really often want to express your algorithm in a way that it matches the layout and the opportunities for speed on the hardware. So if you really focus more on performance and less on portability, you say, look, I want to know what the hardware is doing. I will tailor my algorithm, the structure, and the actual implementation to match the underlying hardware, and that will always drive you, if done well, that'll drive you to a more performing algorithm, but it will absolutely be specific to that piece of hardware. So it is like the slides back here show, can we get maximal portability and maximal performance? Probably not. It's a compromise. Do you want to so if you're working with large software applications, analysis tools that are huge, and the real goal of your application is to for engineers and scientists to analyze underlying large physical systems, you want your software to be stable and well validated. So you have invested a lot of time and effort in reproducibility and the overall usability of the software. And as the hardware changes, you don't want to adjust that software very much typically because it's expensive and then you have to revalidate. And so you're looking, in the application area, you're often looking for portability, maybe a little more than performance. You want it to perform well, but you're not typically willing to invest very much in custom performance for a particular piece of hardware, a GPU versus a mic. You'd like to get, I'll sacrifice a little GPU performance as long as I can get the same answers on both a mic and a GPU. So my background, my personal interest level is more on the portability, and I'm often quite willing to sacrifice maybe a large amount of performance to get portability and reproducibility across a wide variety of architectures, even with the hope that maybe I can do that not knowing what the ultimate architecture will be. Now that, that's probably not achievable. But so it's a compromise. Do you want portability and performance isn't quite as interesting to you? Or are you on the other scale? I don't care about, I'm willing to recode my algorithm for each new machine that comes along. And it depends on what your ultimate goals are, really, what type of strategy you want to employ there in the long term.
Instead of looking at it as a combined problem, can we separate it?
So I think there is some benefit to exposing more about the hardware. I mean that's why MPI and things like that were successful to begin with. It basically, you had a distributed memory machine. That was something about the hardware, right? And there were people who tried to have sort of a shared memory model on top of a big distributed memory computer. And I think there's some value in knowing that it's a distributed memory computer. And now we have these nodes that are much more complex, and I think exposing some information about that. It doesn't have. I think there has to be some sort of abstraction that fits lots of different kinds of hardware that's appearing. That's why we say accelerator and not just GPU, for example. So I think there's some value to that.
So I saw one more hand go up. We've got 1 minute left. So let's ask a short question.
Just I want to add to what he said. So from the field I came from, we were working on embedded systems, and we always have this data flow graphs that's representing the algorithm, and then you get to an algorithm architecture matching using a scheduler. So I'm just wondering, I think what we're saying is just describe the algorithm in one most natural way that's exposing the parallelism, and then leave the job of customizing it to specific hardware to a scheduler or a synthesizer that will take the algorithm and the architecture and try to fit them together. I think that's maybe what he was talking about, and I'm not sure if this applies that much in what we are doing. Instead of just writing in Cocos or in a specific language, no, let's just go into a graph, representing your algorithm and naturally represent your parallelism, and then eventually this will be proof to whatever architecture you're going to be implemented on, because somebody else will be very experienced in the architecture and know exactly how to make use of this parallelism expressed in the algorithm itself and map it to the architecture.
Okay, well, we've come up on the end of our hour for this panel. I appreciate everyone's questions. Let's thank our panelists. I saw that we lost one. I know that Brian had to leave to catch his ride to the airport. That's why he had to leave just a bit early.